There's an interesting mechanism that occurs when we have an ester with a tertiary alkyl group bonded to the oxygen, like this tert-butyl group here. The mechanism for the hydrolysis is a little bit different than the previous mechanism that we discussed. The products that we predict are still exactly the same, so we have our ester with the tertiary alkyl group in the presence of acid and heat. We get a carboxylic acid and a tertiary alcohol as the product of the reaction. So anytime we're going to make this tertiary alcohol in our reaction, there's a little bit of a different process for the mechanism. We have our ester under acidic conditions. It's still going to protonate from the acid. That gives us this activated ester here. Remember that this activated ester has a resonance structure, which we see here. This resonance structure is important because this is where the mechanism takes a little bit of a different turn. Because we have this carbocation bonded to the oxygen and the tertiary alkyl group, what can happen is that the oxygen can just pull the electrons from that carbon, giving those electrons all in one step right towards that carbocation. That's going to generate our molecule of carboxylic acid right here, plus a tertiary carbocation. We know that tertiary carbocations are reasonably stable. This tertiary carbocation undergoes a substitution from the water. We deprotonate the water, and that gives us our alcohol. Overall, the two products in this reaction are the tertiary alcohol that we made from the tertiary carbocation and our carboxylic acid product. This mechanism happens differently because of the stability of that tertiary carbocation. And in fact, esters where we have the tertiary alkyl groups, these are some of the easiest esters to hydrolyze. So what we're going to look at in this handout is evidence of the tetrahedral intermediate in our nucleophilic acyl substitution reactions. So nucleophilic acyl substitution refers to a nucleophile attacking a carbonyl, like what we see right here in the first step. We know that all of the mechanisms that we've drawn so far have gone through this tetrahedral intermediate. And what this mechanism here is going to show you is it's going to show you how we know that the tetrahedral intermediates are forming. This mechanism is also going to show you why the following never happens in our mechanisms. That is, when we have an ester like this one here, if we have this ester under basic conditions in the presence of a hydroxide ion, the hydroxide ion does not attack that carbonyl, immediately kicking out that ethoxide group. This doesn't happen. We know that it has to go through that tetrahedral intermediate. That's what we've talked about over and over and over in our studies. And that's what this mechanism is going to show you. Because in this mechanism, what we're going to do is we're going to follow this O star, and that's going to represent a radiolabeled oxygen. And a radiolabeled oxygen is going to be a specific isotope of oxygen that we can follow through the course of the reaction. So everywhere I see this O star, that represents that radiolabeled oxygen. So if I go through my mechanism and I highlight everywhere where I see that O star, that's the specific oxygen that we're going to follow. So in the first step of the mechanism, what's going to happen is our hydroxide ion is going to attack the ester, kick the electrons up to the oxygen, and we get this first tetrahedral intermediate. We've talked before about how our reactions are reversible, and so every process in this reaction we're talking about is reversible. So this tetrahedral intermediate can take a few different paths. This tetrahedral intermediate can collapse, and if it kicks out the ethoxy group, we get to this product here. And when we get to this product here, we get a carboxylic acid, and we have that radiolabel on the carbonyl. We know that the next step in this mechanism would be for that ethoxide ion to grab that proton from the very acidic carboxylic acid proton, but we're focused on the oxygen here in this example. This tetrahedral intermediate here could also collapse and kick out that hydroxide ion that just attacked, and that's going to send me right back to this initial ester that I started with. Now, if this negatively charged oxygen hangs around just long enough in solution to encounter a molecule of water, it could protonate. And if it protonates, we then have two OH groups in this tetrahedral intermediate that are equally likely to become deprotonated in order for the mechanism to continue. So if this oxygen gets deprotonated, we go right back to this tetrahedral intermediate. But if, under the conditions of this reaction, it's this other OH that gets deprotonated, we then get to this intermediate. And as this tetrahedral intermediate collapses, we have two pathways we can take. The first pathway is where it collapses and kicks out the ethoxy group. That gets us to this product. This product still contains that radiolabeled oxygen. It's no longer in the carbonyl oxygen. Instead, it's in the OH group of the carboxylic acid. But this is the product here that's key, because this product here no longer has that radiolabel. That radiolabel was lost in the form of a radiolabeled hydroxide ion. And so the fact that we can go through this mechanism, we can start with that radiolabeled oxygen in that carbonyl, and we can end up with some amount of product that has absolutely no radiolabeled oxygen in it, means that during the course of the mechanism, the two oxygens in my tetrahedral intermediate were equivalent. So that in one pathway, I can end up with a product that maintains that radiolabeled oxygen, and in the other pathway, I can end up with a product that loses that radiolabeled oxygen. This is that key intermediate where those OHs of the tetrahedral intermediate are equivalent to one another. And I can have two pathways that occur from that product, one that keeps that radiolabeled oxygen, the other that completely loses that radiolabeled oxygen.